Okay, we're going to go ahead and look a little bit. We did already looked in 1.3a at strategies for finding limits analytically. And so remember, the first thing you always try to do is do a direct substitution. So once you see a limit, try to take the value that x is approaching and do a direct substitution and see if you get some value for that. If you don't, if you get something like 0 over 0, what that means is we can actually manipulate our information and simplify the expression, or in this case, use some kind of special trig limit in order to allow us to find the limit if it exists. And so that's what we're doing today. We're going to look at special trig limits. Then we're going to go through a few more examples. You'll see the complex fractions. We mentioned that in the other video, and so we're going to look at an example of that. But let's jump in and look at the special trig limits here. So there's two special trig limits that we want to be familiar with, one that deals with sine, one that deals with cosine. So the first one we're going to look at is the one that deals with sine. And so if I remove this, you can see it, and that is the limit as x approaches 0 of sine x over x, and that would equal 1. Right? And so that's something that we'll want to memorize, is the limit as x approaches 0 of sine x over x, that equals 1. But we can play off of that a little bit, and you'll see a lot of examples I have here don't look exactly like that. And so there's ways to play off of that a little bit, and so we'll look at a real basic example first, but we'll look at some things like over here to the left where I have red starred that allows us to look at problems using that special trig limit, but in a really different way. And so that's we'll look at in just a moment. Okay, so let's look at a base example of this first one right here. So that takes us right over to this one right here. So we have a limit as x approaches 0 of sine 4x over x. So what we do first is we try a direct substitution, and what you end up getting is you end up getting sine of 0. 0 times 4 is 0. That's where I got that, over 0. Now, sine of 0 is 0. And so what we end up getting is we get 0 over 0, which isn't that uncommon in calculus. And so that's something that, though, we can work with. What that tells me is I can go ahead and simplify this using some of our strategies. We tried direct substitution, it didn't work. This isn't really a polynomial, so we're not going to try to factor. There's no radicals, there's no rationalization. It's not complex, and we're not doing complex. So there's a trig. I mean, we see a trig function here. So obviously, we're probably going to use some type of trig identity that we're learning here. And so that's what we're going to do. Eventually, when we get that 0 over 0, we're going to L'Hopital it. Okay, so again, that I keep bringing it up because I want to put it in your mind now, even though it's something that we'll do later. And so as we look at this, what we want to recognize is we have the sine of 4x over x, and hopefully we can connect it to this sine x. So to do this, what we can do is we can actually simply look at the coefficients that are in front of each x. And so what we have here is we have a 4 in front of this x, and we have a 1 in front of that x. And once we identify that the identity we're looking at is the sine x over x identity, then really all we need to do is take the ratio of the coefficients. And so in this case, it's simply 4. Okay, now if I'll show you exactly how to do. That's going to be the quick way of doing it. Okay, so that's how we're going to look at it. But let me show you like why it works. Because you're like, well, that just seems like I made it up. And so let's go ahead and look at this again. But now what I'm going to do is instead of 4x, I'm going to say let u equal 4x. And so this is like a u substitution type of thing. And so we do that in math a lot. So we have instead of 4x, we're going to put a u. Now on the bottom, we had an x, right? And so we want to put it in terms of u. And so if I rearrange this, let's say divide by 4, what I get is I get 1/4 u, or u over 4, equals x. So wherever I see an x, I can put 1/4 u. Okay, and so that's what we have there. So let's take a look at this. Now remember way back, now first off, this is now it's a sort of a complex. So what we have is a fraction inside of a fraction. So I'm going to clean this up just a little. And so in doing so, that brings, keep it, change it, flip it, KFC, those kind of things that you've learned. And so we go ahead and we rewrite this in this type of manner. Now, if you remember what we did with some of our properties, we said if we have a constant that's inside, then that constant can be looked at as something that could be moved outside. So you could technically look at something like this. Okay, now this is where I want to get to. Because now if you take a look at this, now I know I didn't use x. Up here I used x for our formula, but x is arbitrary. I mean, we can use whatever variable you want. So u, we can say it's just x again or whatever, but what I have boxed now is our identity. And so what we need to memorize is that the limit as x approaches 0 of sine x over x, it is 1. And so what we have here is we technically have 4 times 1, which is 4. Okay? Now, we got that answer about an hour and a half ago, doing it a little bit quicker way. So that's obviously what we're going to do. But I want to show you the math of where it comes from, not just a shortcut, quick way of doing it and then sort of abandoning the why is it for type of thing. So we really won't be doing it much this long way anymore, but it's good to see how we can accomplish that. So let's go ahead and I'm going to clear some of this off so we can see. And we're going to look at the second identity and get that in. Now, we don't use the second identity quite as much, let's say, in AP Calc. And so that's why you can see there's not as many examples of it. We're going to be using the sine one quite a bit. But here's the second one that we need to get memorized. And that's the limit as x approaches 0, 1 minus cosine x over x equals 0. And so we want to memorize those two. Those are two good flashcard type of identities that we want to get down. So these two right here. So we got to get those sort of memorized. And then we got to learn, how do we use them? So we've looked at how to use it there. Let's go ahead and look at the example over here with tangent really quick. That's another sort of basic one. When we look at the one with tangent, obviously we don't have a tangent identity, but what we got to remember from pre-calc is that tangent has a quotient identity to it. And so tangent of x is the same thing as sine x over cosine of x. So I could rewrite my numerator as sine x over cosine x. Now, when I do that, technically it's over x, right? But we're going to keep that. That's our numerator. So keep it, change it, and then we'll flip it. So it'll look something like this, or I'm running into that other problem. And then if I sort of rearrange it just a little bit, in other words, just use commutative property down on the bottom, I can get that x underneath the sine x, and then I can put the cosine underneath the 1. Now, the reason I want to do this is through a direct substitution that when we started, we end up getting 0 over 0. Tangent of 0 is 0, and obviously x being 0 is 0. So where does our simplification come from? And it comes from this concept right here, because what's the issue is the 0 in the denominator. So that x value right there in the denominator, I would like to remedy that issue. And to do that is through using our trig identities. And so what we're doing is we have the limit as x approaches 0 of this product. And remember what we did with our properties. The limit of a product is the product of their limits. And so I just need to find the limit of each one individually. So like, what's the limit of this one that I have boxed? And that's our identity. That's what you need to memorize. So here I say, well, that's just 1. And then on the second one, nothing stops me from plugging in 0 into cosine. The cosine of 0, I can do that. That's not that's not going to be a 0, in other words. Sine of 0 was the issue if it was on the bottom. But here, cosine of 0 is simply 1. And so we get 1 times 1, which is 1. And so our value for this limit up here of tangent would be 1. Okay, so that's how you can manipulate the some of this trig identities and what we learned in pre-calc with some of our basic trig identities there, and how we use these trig identities of limits to help us find and evaluate these limits, these trig limits. Now, let's go ahead and look at what's in the box over here to the left. What we have is the limit as x approaches 0 of sine ax over x equals a. So this is what I was talking about. Now, I'm going to expand that a little bit and even put a b here now. And so what it is it's simply a over b. Now, I want to even expand it another one for you. I'm going to put a c out in front. And now what it is it's simply c times a over b. So what I'm saying here is that we've got constants that could be out in front here. We got coefficients inside and coefficients on the bottom. Once you identify that it's the special trig limit of sine x over x, then what we really are consumed with is really the coefficients of the outside and the coefficients of the inside of sine. And so really the answer is just c times a over b, whatever that could be. The bottom's the same way. And again, this is something we can definitely work through and prove why this is. For right now, we're just learning sort of the shortcut. So we have the limit as x approaches 0 of sine ax over sine bx. And what we can do, just real quickly show you this one, just so, again, I'm not just taking it for granted. If I go ahead and put an x underneath this, I'm just separating this and then put an x up here. Would you agree the x's would cancel? So I haven't really changed any value here. But what I've done now is I've set up two separate limits, especially the first one. This one's going to look very familiar to you. And so what we have is there's our special trig limit. And so the answer to that is simply whatever a is, a over 1 kind of thing. Now, even the second one here, and you'll see that in this example or second example right there, is that the reciprocal of 1 is simply 1. So the reciprocal of the limit as x approaches 0 of sine x over x is also going to be 1. So in other words, if I can flip these two, means I should be able to flip that one. Okay, and so what we have is we would end up having 1. Now, look at the cosine one, though. If I said something like, what's the limit as x approaches 0 of x over 1 minus cosine x? Excuse me here, pin's not working really well. There we go. Okay, now that's a totally different thing, because if you flip 0, we're running into some problems because we got 0 in the denominator. So it does not apply for the second special trig limit as much as it does the first one. And again, we don't see a lot with the cosine one, but it is something that we need to be familiar with. So what we have here is, again, all we need to do is just look at the coefficients. A over B is our answer. Now, if there was a C in front and a D, then it'd simply be C times A and D times B. And that would be our ratio for that limit. So if you look at the first example, the limit as x approaches 0 of sine 2x over sine 4x. Let's look at that real quick. On this one right here, if I try a direct substitution, always try a direct substitution first, because sometimes it looks like it's going to be a special trig limit, and it's not. You can actually plug it in, and we'll see one of those in just a moment. Okay, but in this case, if I do plug it in, I end up getting 0 over 0. So sine of 0 over sine of 0 is 0 over 0. Okay, so what I want to do is I want to go ahead and look at this as one of my special trig limits. And I recognize it's a sine one, and so we're concerned with really just the coefficients. I have a 1 out in front. That's not going to be affecting anything, but I have a 2 here, and then a 4 down here. And again, I have a 1 out front, so it doesn't do much. So what I have is technically 2 over 4. And that is 1/2. And that's our limit for that one. Isn't that nice? I mean, it's obviously cutting out a lot of math, but man, it's something that as an AP student we got to be able to work quickly, and so we will learn some shortcuts for these kind of thing. And so this is one of them. If you look at the next example, this is sort of like that one. We have the limit as x approaches 0 of x over sine 4x. That's not really set up like our flashcard would say, like at the top here. It's not really set up like what we would memorize, but we want to play off of that. Okay, we don't want to be too robotic, and we understand that the reciprocal of 1 is still okay. So if the reciprocal of sine x over x is still going to be, so in other words, I could have made a flashcard that was x over sine x, and it would also equal 1. Okay, so both of them are really derived the same way. So we look at something like this one, and we go, well, what's in front of the x is a 1, and what's in front of my x down here? So again, we look at the coefficients of either the variable or the function. And so what we have is 1 over 4, and that is your limit. Isn't that nice? Okay, looking at the last example, what we do is, this is what a tendency we have as students, especially in AP, is that we want to go very quickly. And so I get a lot of students that want to put 2 over 3 as their answer. And 2 over 3 would be a great answer if x was approaching 0. So don't get so in a hurry, okay? It's one of those be quick but don't be in a hurry type of thing that we neglect to try the direct substitution. So in this problem right here, really what we need to be doing is we need to be doing a direct substitution. So we end up getting the sine of 2 pi, which is 0, over 3 pi. And so sine of 2 pi, and again, just real quick, we have time. If I draw sine of 2 pi is 0. So I end up getting 0 over 3 pi, and that's okay. 0 divided by 3 pi is 0. And so our limit for that one would be 0. So that's a direct substitution, not a special trig limit. Okay, really quickly, to finish these off, we have these and we have some diving boards. So I'm going to go very quickly. So again, pause, work through them a little bit. The complex ones right here, so that may be one you want to take a look at as I go through. You might want to watch what I do, but you can try it. You just have to simplify the complex, which is what you've done in maybe some previous classes. So let's look here. The limit as x approaches 0 of sine x over 2 over x. Now, I wrote this one just because I wanted to make sure we understood what the coefficient of x over 2 is. You could rewrite this. You definitely don't have to. But just to make sure you see that, you see the coefficient's 1/2. So x over 2 is just 1/2 in front. And this is a special trig limit. And so what we have is simply 1/2 because I look at the coefficients, 1/2 over 1. And that leaves me with 1/2. Looking at the second one, now I've done these enough that I remember tangent's going to be a lot like sine, so I can actually look at the coefficients, and it's going to be 2 over 1, or my answer is going to be 2. Now, if you want, you can, like, where did I get that? You can convert your tangent over to sine 2x over cosine 2x. So keep it, change it, flip it. Then we'd regroup like these two would be above and below each other. So notice that's our special trig limit. And so we get 2 times 1 over cosine 2x. And then if I plug in 0, I get cosine of 0. Cosine of 0 is 1. 2 times 1. Hey, guess what? We get 2. But again, 45 minutes ago, we had 2, just because I remember the tangent is going to be very similar to the sine when it comes to coefficients. Okay, so I'm going to go ahead and clear that off. So pause it if you need to write that stuff down. Okay, let's go ahead and look at the next one. Now, as we do, what's the first thing that we always try to do is we always try a direct substitution. And so that's what we're going to do here is we're going to plug in -1. So we end up getting 2 plus 1, okay, minus 3. And so that ends up being 0. So you can probably anticipate maybe what's going to happen here, but let's make sure. We get 1 plus 2 minus 3, and guess what? Yep, you were right. We got 0, 0. It just simply means we just need to go to work. And so now, again, when we see 0, 0, this one's going to be so easy for L'Hopital. So we'll end up L'Hopital in this in the future. But for right now, we got to do what we know how to do, and that is through factoring. So we've got a bottoms up on the top. We got a bottoms up on the bottom, but shortcut, so it goes a little faster. And so we can go to a double bubble on the bottom. On the top, if you want, you can get your factoring x in if it helps you get organized. So we got -6. We want to find factors at -1. So -3 and a +2, and then take your a value. And so that allows me to get my double bubble on top. And so on top, we end up having bottoms up here, 2x minus 3. This one simplifies to be x plus 1. On the bottom, we can probably do that just in our heads. So we get x minus 3x plus 1. And there's our factoring. Now, once we get to factoring, what we're looking for is to eliminate something vertically. So to cancel something vertically, and we can get rid of this x plus 1. And so we will cancel those vertically. And then it should allow us to plug in a -1. And so if I plug in -1, I get -5 on top. And then -1 minus 3 is -4 on the bottom. And so that makes it a +1 1/4. And so we're looking for a +1 1/4, which is D, multiple choice. There we go. Okay, very good. Looking at the next one up here, it is a trig one, but it's not a trig identity because we always look for a direct substitution. So we want to figure out what in the world is the cosine of -pi. My parentheses aren't looking very good today. There we go. And so if you're a little unsure how to do the negative for cosine and sine, things like that. So cosine, remember, starts like this. I'll give you a little graph this way because we want to go this way on this one. So there's your -pi/2. And there's your -pi. So it's like, well, how far down does that go? Well, our range is -1 to 1. So this is going to be -1. That's what it is. Okay. And it's just direct substitution. So D is our answer, -1. Now look at the last one. This is going to be the one that we haven't really looked at, and that is because it's a complex one. So if we do a direct substitution, we end up getting 0 over 0. Okay. So now we got to go to work. And it's like, well, how do I handle this? If hopefully what you can recall from maybe an earlier class of some sort is when you have complex fractions, really what you want to do is let's just ignore or pretend the bottom isn't even there, and let's just simplify the numerator. You do the same thing with the denominator if there's a fractions there. So let's just focus on the numerator. We need to create common denominators so that we can combine these two expressions into one. So to do that, we factor fractions first, okay? And so in this case, there's not much to factor, but what we have is our factors are x plus 4 and then 4 for the right one. So it looks like the left one needs a 4, so I need a factor of 4 on the left expression. And then on the right expression, I'll need the whole entire bubble. So I have this 4 here, but I need x plus 4 as it's missing that. And then whatever you do the bottom, you got to do the top. So I'll need to put that x plus 4 on the top. Now, before I go too much further, you want to be careful on these, and hopefully you remember why. But x plus 4 is a quantity. This is a grouping symbol. The fraction bar is a grouping symbol. So if it helps put bubbles, but when I combine these two or squish these two together, that minus sign needs to be distributed through. So sometimes I notice that students will forget to distribute that, but just keep that in your mind. And again, remember what we're trying to do. The issue that we have here is the x on the bottom, right? If I plug 0 into x in the denominator, that's my issue. So I want to get rid of it. So I'm manipulating the numerator so I can get rid of the x. So I should be getting some type of x in the numerator so I can cancel. And that's what we get here. The denominator, just leave it. I wouldn't distribute, much like we said with rationalization. Just leave everything unsimplified until you have to simplify. So what we get is we get the opposite of x in my numerator and 4 times the quantity x plus 4 in the denominator. And then what I have is there's my numerator, okay? So it's simplified. So keep it, change it, flip it. Now, if the denominator had fractions down here, I would ignore the numerator and make sure the denominator is one single term. So simplify, combine those like terms. Then you can keep it, change it, flip it. So x, remember x is the same thing as x over 1, so we flip it and we get here. Well, look at that, isn't it? It's just like magic. Is that our x's are going to be able to cancel. Now, don't forget about that negative here. It's still hanging in there. And so what we're going to have is we're going to have -1 in the numerator, and we'll have 4x plus 4 in the denominator. But that should allow me now to take that 0. Remember, our goal is to always get to a direct substitution if possible. So that should allow me to get to a direct substitution. And what you'll notice is I get -1 on top, and I get 4 times 4, 16 on the bottom. So -1/16 is our value. So that would be a problem. We could also L'Hopital down the road, but for right now, using complex would be the idea. The last two that I want to look at are our diving board functions. So remember graphically what these look like. This first one right here, just to show you a real quick graph, is that if I plug things in that are bigger than 0, I should get positive values, and specifically +1. And if I plug things in less than 0, I should be getting -1 as my answer. So this is called diving board function. Can't plug in 0, it's undefined at 0 kind of thing. But you do get like 0 over 0 type of thing. Now, if you look at this problem really quickly, what we have is we always try a direct substitution. So if I just directly substitute this in, 5, I get the absolute value of 5 kind of thing. It'll let me write. There we go. So I get the absolute value of 5 over 5, which is +1. Okay, so that's where we're at. Now, when we take a look at the second one, the one on the bottom here, the issue with the one on the bottom is when I try to plug in 5 for this one on the bottom, I end up getting 0 over 0. Okay, now this is a little different graph. Okay, so it's not the same graph. It looks similar, but it's shifted. But if we go over to 5, you can see why it's 1. The limit as I approach from the left and as I approach from the right is 1. That's why we got the answer for the first one. But on the second one, what we have graphically, and again, we don't have to graph it, but it's good to see, is we should be at 5, we should have issues. So we should have it being 1 if it's bigger than 5, and -1 if it's less than 5. So we got 1 here and -1 there. Okay, and you can prove that by plug in 0 and see what you get. You should end up getting -1 when you do that. Okay, so graphically you can sort of see what in the world's the limit. Well, the limit from the left is -1, and the limit from the right is +1. So the limit shouldn't exist here. And so as we do this algebraically, we gotta consider that absolute values have two cases. And so what we've got to consider is what is the limit as x approaches 5 from the right-hand side, which means when I plug in something bigger than 5, so 5.5, I should end up getting a positive in here, which means it is the positive case, or what we talk about is case 1, and that is where you just simply drop the absolute values and solve by the definition of an absolute value, which is a piecewise function. However, if I do the other side limit, the two-sided, remember, we got to check them both. If I go from the left-hand side, so instead of a value like 5.5, we're plugging in a number like 4.5, something that's left of 5. So 4.5 minus 5 is negative. So the value we get inside is negative. Now you're probably thinking, well, it's an absolute value, should make it positive. You're right. However, we're looking at it as two different cases. So rather than the absolute value sign being there, how do I write it without an absolute value sign? And that means I want the complete opposite of what's inside. And so if what's inside is x minus 5, I need the complete opposite of x minus 5, which you can distribute if you wanted, okay, and x minus 5 on the bottom. Okay, so it looks like this. Now, I don't really need to distribute because what we have is this is going to cancel with that, and I'm left with -1. And so you can see those are our two values. And so if I'm checking the limit at 5 for this, we're running into an issue because the limit from the left doesn't equal the limit from the right. Now, any other value is fine. So instead of 5, if I do 2, I end up getting the absolute value of -3 on the top over -3. And then what's the absolute value of -3? Well, that should be 3. And then I get -3 on the bottom. And then there we go, we get -1 as our answer. So direct substitution works. Okay, and that finishes off 1.3b. So that's our whole lesson on evaluating limits analytically.